Then correlation or regression. How to use this correlation regression. The difference of that.
Can you hear me? Right. So today we will talk about how to study correlation. And you often use the word correlation in your day-to-day deliberations. And often you are tempted to study correlation maybe between age and sex to some part of the disease or some aspect of the disease. You may like to study correlation between disease severity and maybe outcome. Often I see thesis or I hear people who have published in their paper, and they will say that we have studied correlation between CRP and outcome, or we studied correlation between leukocytosis or leukocyte count and CRP. Maybe all of these things I keep hearing. Then when I ask them in interview, very good, you studied correlation. What was the correlation coefficient? then they will start looking around. Which means they did not even know how to quantify or how to study correlation. So this is why I thought this is very important to for every doctor to know or every researcher to know. Whenever you measure two or more factors or variables in a group of patients, they can be examined whether they correlate or not. So if you are measuring age and you are measuring, let us say, strength, you will measure it in every individual. And if you want to see whether age has any relationship with strength of muscles or not, then you are studying correlation. So, important thing is that in every member of the group, you measure two or more variables. Then only you will think of correlating, right? It is not that you will measure something in treated and something not, some people not treated. Then you are not talking of correlation. Then you are talking whether treatment makes a difference or not. If it is a question which can be slightly modified, if you have a treatment, you can give different doses and say whether there is relationship between the dose and effect or not. But that is not correlation. Correlation is when you measure two or more factors in the same individuals and a whole number of individuals, and you want to see whether they go with each other or not, or they have any relationship or not. Then only you are measuring correlation. So correlation is basically measuring relationship between two variables. Are they related, not related? That's the question. And usually these two variables are observed as they exist in nature. You are not changing it, you are not treating, you are not trying to manipulate or trying to control, but you usually do it as an observational study. So, measure which is going to quantify this, and whenever you do this, you must express this in correlation coefficient. So, if you have two characteristics x and y, then you correlate x and y and measure what is called correlation coefficient. And that coefficient gives you magnitude of relationship, direction of relationship, and what type of correlation coefficient you will use will depend on what type of data you have. When I say what type of data, what do I mean? Quantitative or qualitative, categorical or continuous, or numerical or categorical. That is the kind of classification we have in mind of the data. And two most commonly used correlation coefficients are Pearson's R, or R is written in small, R is written in capital. Do you remember where? When we do regression, right? So this Pearson's correlation coefficient traditionally is written in small r, or you can use Spearman rank correlation. We'll talk about that later, which is written in Greek letter rho. So that is also, this is R, that is rho, RHO, rho. First thing you do is you have to do a scatter plot between whatever two variables you want to correlate. And usually the predictor variable, you keep it in, that is what you did in regression in x-axis, and in y-axis you keep outcome variable. But when you are doing correlation, it doesn't matter, because no matter whether you keep x or y, you change it, still you will get the same correlation. We can see that. And then, of course, you won't do the graphing. Computer will do it for you. But remember, if you were graphing manually, you have to look at what values are there. Whole range of values should be captured. And then for each pair of scores, you have to find an intersection. So you will put a dot there. Now computer does it. So this also called dot plot or scatter plot. We did that last time, and you can see the distribution of the dots and think whether there is linear relationship or not. We did it last time when we were discussing about regression. So just by looking at the plot or graph or dot plot, you can say what is the direction of relationship. And all of you can probably make it out. We say positive correlation if there is increase in one variable shows proportionate increase in another variable. So both are increasing in the same direction. If on the other hand, if increase in one variable shows decrease in another variable, it can happen, no? One variable increases. For example, in Glasgow Coma scale, when you reach 15, means patient is fully conscious, right? So if we want to correlate volume of hematoma in intracerebral hemorrhage with Glasgow Coma scale, as volume will increase, what will happen to Glasgow Coma scale? It will decrease because it won't remain 15. It will go to 12, maybe 11, 10, or in worst cases even up to 3, right? So there are many situations when increase in one is associated with decrease in another. There is nothing wrong in this. This is the nature of relationship between the variables. Bigger hematoma, bigger volume of blood in the brain will cause much more decrease in consciousness. So, therefore, you have to just see the plot and infer whether there is positive correlation or negative correlation. So this is how positive correlation will look like. You see, if, as you can see, as values increase in x-axis, values increase in y-axis also. So you get an upward sloping figure. That is to say that higher scores on x is associated with higher scores on y. And lower scores on x are associated with lower scores on y. So that is what you see when this is example is father's height versus son's height. There is, as you can see, height of father increasing, son's height also increasing, right? So there is correlation. Scatter plot will show this, and similarly a negative correlation. Again, data points will show that when the value is increasing in x-axis, there is a decrease in value of y-axis variable. So this is how it will show up. So there is, this is education, level of education versus prejudice score. So how much prejudice, lower the education, more the prejudice. I think here, if you in Jharkhand setting, if you think, then degree to which people believe in dying will be related to education. No, more the education, less the belief on this what you call dying in villages. When there is no correlation, then plot will have no linearity. As you can see, it will be scattered all over. A perfect correlation will be what I have shown in previous day. All the data points will fall in one line, right? This is a perfect correlation. And if you have data which is continuous, which means there is numerical data in one variable, numerical data in another variable. What is other than numerical? Like dichotomous data. That is not numerical because it is alive, dead. It may be a situation like remission or no remission. So those are not numerical data. There may be ranked data, stage 1, 2, 3, 4. That also we don't call numerical because there are only 4 categories, for example. Those are called categorical data. But when there are numbers which have a wide range, and people say that if your scale has a range which goes beyond 7, then you can treat that as continuous data. So one condition which is there to do Pearson's R is that they should be numerical data, also called continuous data, also called scale data. In SPSS, it is called scale data. And second assumption is that it should be linear relationship. That we talked about the other day also. And if anybody remembers, I showed you example of non-linear data also. What was that? You recall I said, you see, this is not linear. Here, even U-shaped curve, right? And that was relationship showing between, it was in stroke patient, relationship between systolic blood pressure and proportion of death. So as blood pressure was going down, people were dying. As it was going up, people were dying more frequently. So it was U-shaped relationships. All relationships are not linear. Pearson's R is to be used only when there is a linear relationship. Then the question is about, we also say that they should not be only numerical data. Ideally, they should be normally distributed in, bell-shaped distribution. And then the question comes describing the strength of relationship. Strength of relationship in case of Pearson R is described by a number. And that number ranges from -1 to +1. +1 is the strongest relationship which is possible. And -1 is, you don't say, no, this is a question for new people. So typical answer from the new students will be -1 means weakest relationship. No, this is also the strongest relationship because only difference is in +1, the relationship is positive, it is positive correlation, whereas in -1, the relationship is negative, right? So negative correlation, but both are equally strong. +1 and -1, both are equally strong relationship. Only difference is that there is one is positive, the other is negative. Then what is a weak relationship? If Pearson R is from 0 to 0.3 or 0 to -0.3, so magnitude either side is weak relationship. Moderate relationship, when the numerical value is from 0.3 to 0.7, which means it can be +0.3 to +0.7 or -0.3 to -0.7. And whenever there is value is above 0.7, either plus or minus, then we call it a strong relationship. So the plus or minus indicates the direction of relationship and the number indicates the strength of relationship. And obviously 0 means no relationship. Perfect relationship, but negative correlation is -1. Perfect relationship, positive correlation +1. So closer to 1, stronger the relationship. Now, as you can see, when the data is distributed in a haphazard manner, correlation here is 0.05. So close to 0. But when they are very much linear, then as you can see, it is very close to 1.99. That is the second panel on the upper one, right hand side. But plus 0.7 or minus 0.7 means it's also a strong relationship, but not as strong as 0.9. But it will also qualify to be called a strong relationship. So if you are taking education versus lifetime earning, that as education increases, lifetime earning also increases. But little bit in the last one, you are saying there is a dip, no? That is for the AIMS people who work in AIMS. They are highly educated, but they don't earn that much. The rest of this is for RIMS people. More educated you are, more lifetime earning you have, right? So I have already told you interpretation of Pearson R. Now, sometimes what happens is that, say for example, if I wanted to study correlation between number of classes attended and number of marks obtained in the exam, right? So people often said, do it in AIMS students, undergraduate students. I said, no, this is not a good population. Why? Irrespective of whether they attend lecture or not, they will score high because they are selected by very stringent exam, very high scoring people. 1 out of 1,000 they have been selected, and many people don't attend any class at all, but still they get very high marks, right? So one example was a student from Ranchi, whom Professor Ramesh, he was a pediatrician here, if you know. He introduced me that he is a Ranchi boy, please look after him. And I won't tell his name, but I used to go to his room and he will be working in his room, not attending classes. So I said, you don't attend any classes, it seems? No, I don't attend any class. So what are you doing? No, I will get good marks, there is no problem. So they actually read the books and get good marks because there is no, he will attend some practical classes, but not the theory classes. The theory classes, they read the books, I can also read the books. So he finally actually joined the IFS because he later on decided doctor, not a very glamorous profession. So he decided to go for different profession. Anyway, so if you do some study only in the AIMS people, you will get something which you see in the circle there. That, the circle is for those who attended, let's say, large number of classes and they got very good marks also, right? But if you don't have a good range, then you will end up something like, I think the second one, or some of part of it will be curtailed. So if you cut down some part of the graph, then the line which you will draw will not be as strong because there will be no pull from the top. You will get a correlation which will be around moderate. But if you have the wide range, like if you do the study in RIMS, you have wide range of students' ability, then you get the strongest possible correlation because they represent the full range. So you can imagine any graph which I show, if you cut the middle part of it and again do the graphing and correlation, you will get weak correlation because they are all scattered here and there, they are all in one area. But if you have the wide scatter, then only you can draw a line which will be very clearly showing a strong correlation. So this is called restriction of range. This plagues all the educational studies. They often have very restricted range because they have only one kind of students. So that is a reason why even if there is a good correlation like between number of classes and scores in the exam, you will get poor correlation because you don't have good range of students. So you have to always keep that in mind. So range of scores will influence Pearson's R. So this is what it shows. I think what this circle is something like here, though in this whole range there is a strong relationship, right? The first figure, there is a strong relationship. But if you only take top of the score like AIMS students, then you get circle like this, which shows R equal to 0.08. Whereas here, there is hardly any relationship. But if you take only top circle, then you get this, which shows a strong relation, 0.85. So the key thing about having true picture of relationship or the correlation is have a wide range of parameters. Yesterday I was reviewing a paper which is on persistent neurological symptoms at 12 months after COVID. And they say that we didn't get very good correlation, possibly because we had a wide range of patients, from outpatient to inpatient to ICU, all kinds of patients. So I have given comment in my review that actually that should have given you stronger relationship because you had wide range of people. Restriction of range gives you weaker correlation. This is the point I am trying to make. Okay. Now, one thing you should know, that correlation may be very high. For example, what do you think about correlation between petrol prices and literacy level in India? High, moderate or low? Petrol prices in India and literacy level over last 50 years from the time of independence, 75 years. High? Why do you say so? Purchasing literacy level, I mean petrol prices. Oh, you mean to say that because they are, I'm saying that literacy, just able to read and write, that is increasing. Or I could also ask, what do you think about mean life expectancy and petrol prices? Correlation is small, moderate or high? Petrol prices are increasing, right? And life expectancy is also increasing. You are measuring everything in India. So in India is means you are measuring environment within India, high correlation. So does it mean that petrol prices are causing increasing longevity? No. So that is what it says. Correlation does not mean causation. Right? So you have to have strong reason to believe that one may be cause of another. It may not be necessarily the cause, but don't go with the idea that correlation exists, that means one is cause of the other. So it can tell you strength of relationship, direction of relationship, but not the nature of relationship. All these things may be actually driven by a third variable. For example, longevity is increasing, petrol prices are increasing. That all may be a result of strengthening of economy, which is affecting all of this, both of these. So there is, the reason I brought this is that before you do regression, and we discussed that last time, you must do correlation. So before launching on regression, whatever variables are under consideration, you first look at correlation coefficient between the all possible combination of two variables. And I will show that to you later. And regression coefficient is actually can be equal to Pearson's correlation coefficient multiplied by standard deviation dependent variable divided by standard deviation of independent variable. It can be, there is good correlation, a good, you can say, in a relationship between regression coefficient and Pearson's R, because both are based on linear relationship, both are meant for continuous data. So not difficult to find out what is the equation between regression coefficient and correlation coefficient. But regression coefficient has a different meaning, because there is a relationship between predictor variable and outcome variable. We are not talking about that here, right? Amount of rice you take and amount of dal you take may be highly correlated, isn't it? But not one is predictor and the other is outcome, right? Therefore, relationship may be whether you plot rice versus dal or dal versus rice, correlation will come the same. But one is not predicting the other or causing the other, and therefore that is not, we are not talking about causation or prediction, but we are talking about just relationship. I will come to this, I will repeat it again. So R being Pearson correlation coefficient, you can convert or you can deduce R, regression coefficient from correlation coefficient. So what are the similarities between correlation and regression? One is, from regression also you are able to find out direction and strength of relationship, if you remember last time, and both work for numeric variables or continuous variables. Whenever correlation is negative, regression slope will also be negative. Whenever correlation is positive, regression slope will also be positive. So you remember regression equation was also drawing a line. Correlation is also drawing a line, and both can be drawn on scatter plot. So similarly, so they give almost the same idea. And I don't know whether I told you, yes, we discussed this briefly. If you remember R square, there was sum of squares, regression and residual, then total. When we said sum of square regression divided by total, we got R square. You remember that? We can do this again. So that tells you how much is the variability, or what range of data is explained by the predictor variable. Same is the interpretation of square of correlation coefficient, which is also can be denoted by small r square. That is proportion of variation in one variable explained by another variable is the same interpretation as we did for r square in regression. What are the differences? Regression attempts to establish how change in x causes change in y. So there is a kind of relationship of dependence of one to the other. Whereas in correlation, there is no such relationship. So you can swap the variables. You can plot x on x-axis, y on y-axis, y on y-axis. You can interchange. Whatever was on y-axis, make it x-axis. Still you get the same correlation, because it is not thinking about dependence on each other. It is not about one explaining the other or one causing the other, right? Or one predicting the other. There is no such relationship. The other thing is, that is little more, you can say, nuanced part of this interpretation. Regression assumes that x means the independent variable is fixed with no error. There is no error in measurement of x. For example, if you want to look at dose, how much dose of medicine causes how much effect, then dose you are fixing. You are deciding the different doses. It is not that it is being randomly picked up. You decide this dose, this dose, this dose, this dose. I will use these 4 or 5 doses or 10 doses. That is your decision. You are fixing it. The effect is not in your hand, right? It happens because of biological relationship between the dose of the medicine and whatever effect you see. Similarly, if you want to see whether temperature in malaria is associated with level of consciousness. Well, temperature you are measuring, and you may even conduct, let's say, and you are measuring also this. You can see whether one is dependent on the other, which will be regression. But if you don't think one is dependent on the other, then it can be correlation. So it depends on the relationship. That is the last thing, which is the difference between correlation and regression is correlation is one figure. We said 0.7, 0.8. Regression is the whole equation. You have to have constant or without constant, whatever it is, plus some regression coefficient multiplied by some variable. So it is an expression which is like an equation, whereas correlation is only one figure. Now I will show you some. First, read the biology of this. What do you think? Is there a relationship between one versus the other which you want to exploit? But I told you that will lead you to regression. But before you do regression, must do correlation, right? And I will, perhaps at some stage, I will tell you why to do this. I think that will be the last slide, but I will show you some examples. I'm going to use my data. We had conducted a biomarker study. Don't look at the names. I'm not supposed to show you the names. But this is patients with intracerebral hemorrhage. We have looked at clinical variables, radiological variables, and biomarkers. 5 biomarkers we wanted to study in this. This was a project funded by Department of Biotechnology, and we also wanted to see what is the outcome. And we had a lot of variables. You can see 242 variables. And obviously, we should not study 242 variables. If we wanted to study really well, then the formula I told you for 242 variables, what should be my sample size? 2420, 2420. We said 10 patients per variable, right? But we were really not interested to study every one of them. Some are measures of income. In India, if you want to measure income and ask people, do you get correct figure or not? You won't get correct figure, because they will start thinking, what should I say so that I get maximum benefit, right? If I say less number, then I get benefit, or more number will give me benefit. So they will underestimate or overestimate, and poor people can't even tell you what is the income, right? They don't even count. They just count whether they are going to get next meal or not. That's their only concern. They don't know how much income they had in 1 year. So we had asked actually that whether they have these things: electricity in their house, mattress, chair, cot bed, table, some electric fan, and even we went up to internet, refrigerator, computer, cooler, and so on, washing machine, watch clock, bicycles. So this is what we were asking. We are not interested to study that. After all of this, we will convert that into some measure of income, and it will all become one variable. Still, we had, so there are many variables which are not of interest. Some are repetition, so CT scanning, date, time, that is not to be studied. So a lot of variables are not for studies here. Still, we had 1,052 patients whom we have collected data with outcome on practically all of them. So I'm going to, you can decide which correlation you want to see. And First thing is to make a, as I said, scatter plot. And they should be continuous variable. Now what SPSS does is, it gives you different figure. As you can see, this is number. So it is like, what does this denote? It is like, scale, yeah, scale, okay. So it's like a ladder or something, right? So the ladder gives you the idea that they are scale variables. So we have to go and see where do we get the scale variable. We got for time, but time is not of interest. So here you see ICH volume, how much alcohol they were using, number of years, for how many years. So those are scale variables. CRP is scale variable. Leukocyte count is scale variable, right? So let's say you want to see whether intracerebral volume, ICH volume, is, we have to first remove this. That is related to, let's say, CRP. Both are scale variable, and we are going to plot, that is scatter plot. And you see, this is the figures you get. Volume is, as you can see, mostly between 0 to 50, very few 100, very rarely up to 150, 200. Obviously, these people. So we are not sure whether there is, suppose, do you think there is some linear relationship or not? Might be. So if you are not sure, then you ask the computer to draw a line, which means regression variable plot, CRP, and I'm going to change to, let's say, where is my intracerebral volume? These are all different treatments which were given to them. So I can even ICH volume. Doesn't. Here, ICH volume. So if we do this, and we have option. You want to fit a line, linear line? Yes, you can do this. So this is what we have selected. And this is going to give you a line, right? So this is how computer fits a line, and I told you that it tries to get the best fitting line, but this is where it got. Now, we don't know whether it is good correlation, poor correlation. You want to know, and use the correlate command, bivariate correlation. And we said ICH volume and CRP. So these are the two variables we will take, and we will say okay. So it gives you this Pearson correlation. Now, as you can see, there is ICH volume here, CRP here, ICH volume here, CRP here. But basically, there is only one correlation. So you get 0.335 here, 0.335 here. ICH volume to ICH volume, of course, they are same. So there will be correlation of 1. And same for CRP and CRP. But what is of interest is ICH volume and CRP 0.335. And the same thing is coming here, CRP and ICH volume. So everything is repeated here. So that is the, you can say, SPSS weakness, that all the correlation which it will give you, it will repeat. So 0.335, first thing you have to think about is it small, moderate, or large? Or small, mild, what do I say, low, moderate, or strong? Moderate. So 0.3 and to 0.7 we said moderate correlation. So there is moderate correlation. Is it positive correlation or negative correlation? Positive. So more the volume, more is the CRP, right? Then the question will be, whenever you get a figure in your study, which is a result of some analysis, then you have to ask a question. Is it by chance or not? Right? When can it be by chance? If you have a small number, you will get things by chance. So which means if you want to not eliminate, but at least be reasonably sure that it is not by chance, then what do you do? No, so you increase your sample size, but you have conducted a study. Now you have a value 0.335. You want to know whether it is by chance or not, right? Then you do a test, right? Hypothesis test, right? Hypothesis test. What will be the hypothesis? Underlying hypothesis that there is no correlation. Null hypothesis, there is no correlation. If you reject that hypothesis by getting a p-value which is less than, that you have to set, you may say less than 0.01, but if you set it at less than 0.05, then and you get p-value of less than 0.05, then it is unlikely that it is because of chance. It can still be due to chance, but it is unlikely. So that is why what SPSS does is it gives you straight away p-value and says correlation is significant at 0.01 levels, which means it is already given here also, 0.000. Now, I have said earlier also, if you are writing your thesis, don't write 0.000. The reason it gives 0.00, p can never be 0. It has to be something, some number, maybe 0.000001, but whatever it is, it will be there. But what SPSS is unable to do is, first thing is, it can't give you more than 3 figures. That is the limitation of SPSS. Only up to 3 decimal figures it can give you. And what it does is, beyond that, it employs rounding. So if the value is 5 or more, then it gets it rounded to another number, and 0.05 will be shown here, but 0.00005 will not be shown here, right? 0.000, that is what it can go to. If the figure was 0.0005, then, or 0.0006, then SPSS would have done the rounding, which means it will give 0.001. Anything, if next figure is 0.5 or more, then it will round to the closest, it will round it to 1 in the left hand figure. So obviously, it was not 0.0005 or more. That means it was less than 0.0005. If it was 0.0005, the SPSS will give you 0.001. Because it will do the rounding. But it was not 5, it was less than 5. That is why it did not do the rounding. And the figure is 0.000, which means actual figure is less than 0.0005. So you will write it, for the students who are doing thesis, you will write less than 0.0005. Don't write 000. This is another thing I see often in thesis, that they will just copy this SPSS and write it, which is not correct. So it is telling you that p-value is less than 0.0005. That means what is called conventionally statistically significant. That means chance is very unlikely. So 2 things are important. One is the magnitude, the other is it by chance? That p-value will tell you. So p-value is important with every correlation. If p-value is not less than 0.05, then don't care about that correlation, whatever be the magnitude. Unless, but you should think, do I have restriction of range? Or means my experiment is flawed, or really there is no correlation? You must think about that. So that is one thing. Now let us see if there are, you can increase the number of variables by bivariate correlation, and I will take some more. I can take age also. What is the problem in that? Age at the time of admission, age at first stroke. That will be very few people who had one stroke earlier. What is this? Duration between at the onset and admission. And let's see if I have other scale variables. Time taken to reach, time spent on number of years people are taking alcohol for. I think I will take 5. Height, weight is also there. For your out of interest, let me put height and weight also. I have not checked it, and you shouldn't do it unless there is some biological reason for this. But let us see what happens. So now it has given you correlation between all these variables. There is repetition. So once half of the image figure is mirror image of the other half. So you will see a lot of 1, 1, 1. You see 1, 1, 1, 1, 1, 1, all of this. So the upper half, this side is mirror image of this. Same thing is repeated. You see 0.002 here, 0.002 here. 0.000 here, 0.000 here. And whatever is statistically significant at 0.05 level or less, as they have put stars. So let's look at first line. ICH volume, of course, correlates with CRP. There is moderate correlation. Age at admission, there is statistically significant correlation because there is star there. But what do you think? Weak, moderate, or strong? The upper figure you have to take, 0.071. That is the magnitude. Second line is significance, means p-value. N is number of patients involved. So we didn't have some data for this about 20 patients, but 1031 patients we had data. Is it weak correlation, moderate, or strong? Weak correlation. Duration between onset and sampling, no correlation. It should not be. Number of years of using alcohol and ICH volume, practically zero correlation, right? 0.002 as good as. Now, height has a, this is not statistically significant, so don't look at it, right? No point looking at it. This is also statistically not significant, so no point looking at it. Height and weight, there is no correlation with this. So if you look at the magnitude of correlation, you find moderate correlation, maybe slightly here. Weight and height are correlated, 0.3, not a strong correlation. Moderate correlation, 0.3. You see weight here and height here, 0.3. Well, that is not something you are investigating in this. Otherwise, you don't see much correlation here. No. So only correlation you see which is of interest is between intracerebral hemorrhage volume and CRP. This is just one example, but there are many other variables. I told you there are more than 240 variables. We can see a correlation, but I don't want to do that. It will fill up the whole screen. And the reason you have to do it is when you do regression, then you have to be very cautious in putting correlated variable. If two variables are correlated, Say for example, you want to see whether scale of disability is associated with age, intracerebral hemorrhage, and maybe volume of hematoma, and so on. Now, volume of hematoma goes into the calculation of what is called ICH score. So they are correlated. Now, you will be interested, let me see whether disability is associated with volume of hematoma. Bigger hematoma will be more disabled people. So you will be tempted to put it. Similarly, you may say ICH score is a scoring of severity. So more severe the disease, more will be the disability. So why don't we see that also? Now, if you see the two, they will be correlated, I think at least moderately strong, maybe very close to strong correlation. Don't put both variables in the regression, because when two correlated variables are there, then equation goes haywire. So you will find that problem is called multicollinearity. So it will spoil your equation. Regression. This is why this is very important. It is interesting to know regression, but not to jump and do it. You have to do a lot of things before that. Scatter plotting, correlation, and then start thinking about doing regression. And there are many other steps before you jump into regression, which I will come to when we do model building. Any question? You want to see that? There will be a lot of questions, because when you start thinking about, I don't know whether I have platelet count or not. Leukocyte count is there. Of course, these were all hypertensive hemorrhage, so I don't know. So we may not have picked up platelets. So you want to see a correlation between platelets and volume. Volume, no? That has good biology, so you can certainly explore this. Surprising, no correlation. You see, 0.043, which is practically zero, you see significance value 0.186 means correlation. Whatever it is. No, you know what this is, if you had wide range, if you had platelets from 30,000 to 100 and 250,000, then you will get correlation, no? You will see if you, yes, that is a good example of how restriction of range can affect this thing. If you want to see, you can, that is why scatter plot is very important, no? You see, so all the platelet count which you see is from 100,000 to 300,000. Mostly this. You don't have very few which are less than 100,000, right? That is why you don't see it. Suppose, so this lower down, it is missing. The whole graph is about 1,000. So if your platelet is 100,000 or more, then the volume of hematoma has no correlation. It has drawn a line which is horizontal line, means no correlation, zero correlation. So that is what it shows. So good example of how restriction of range can affect correlation. Right. Any other question? blood pressure and what? Volume of hematoma. Of course, there will be correlation, I think. But systolic blood pressure, let me take diastolic blood pressure, which will not be very strongly correlated. Surprising. This is blood pressure at admission, right? So this does not correlate very well. It has statistically significant correlation, but low correlation. SBP and ICH volume also, there is a statistically significant correlation, but low correlation. Not a strong correlation. But if you want to see the outcome, that will be correlating with this. Outcome, I don't know. We may have data on that, but lot of things you can do. Any other question?
Sir, online Dr. Sandhya is asking, so in case of correlated variable, regression should not be done?
No, you have to choose, depending on the knowledge of biology, one of the variable which will enter the regression, not both variables. If two variables are highly correlated, then what are the criteria for choosing? One is biology. The second is which one is easy to get. Third is which one is less subject to error of measurement, right? So more likely to be measured accurately, less hassle, less cost. That is the one which will go into the regression. The other one will not go. Any other question? If not, then no other question. Thank you very much.